Okay, so it's time to start. So, hello everyone. Thanks for attending today's Rocky World discussion. And this is our fifth meeting in this year. And I am Hiro Kurokawa, the moderator for today's discussion. And it is my pleasure to introduce today's speaker, Professor Jun Korenaga. Jun is a professor of the Earth and Planetary Sciences at Yale University and known for their pioneering studies on the mantle evolution and its role in shaping Earth's surface environment. And today he's going to introduce us his recent study on the early volatile evolution of the terrestrial planets. And as our discussion format, we have the 30 to 40 minutes talk by a speaker followed by discussion. And I would like to ask a participant to use your full name on your Zoom name so that we can identify who you are. And also please keep your mic muted, and only when you speak, please turn on your mic and video. So, all right, please, let's move on to the Jun's talk. So, Jun, could you start sharing your screen?
Okay, yeah, and do it right now. Okay, hello everyone. Thank you for the kind introduction. I'm gonna move this around because it's a little okay. Fine. Good. Yeah. So the title of my presentation is the early volatile evolution of terrestrial planets, and this is a very broad topic, so I can only scratch the surface. And what I like to do today is to talk about some of my group's recent work related to this topic, and I also hope to show that these recent studies point to some promising future directions. Okay. So this is the Earth we have today, and as we know, it has just the right amount of carbon dioxide in the atmosphere. Its greenhouse effect keeps Earth's surface at moderate conditions where liquid water can exist, and Earth also has just a right amount of water on surface, so most of continents are above sea level, which facilitates chemical weathering, which is important to modulate the long-term atmospheric compression. Now, the question is, can we explain why we have this kind of planets here from first principles? That is, by thinking what kind of planetary formation and evolution processes have to happen to arrive at a planet like this. So that's an overarching question, and this is the overview of my presentation. And first, I'd like to briefly talk about why answering this question from first principles is so difficult, and then talk about alternative approach based on mantle evolution and its limitations as well. And finally, come back to the first principles approach with an emphasis on the fate of atmosphere during planetary accretion. So ideally, it would be nice if we can explain how a planet like Earth forms from the stage of planetary disks. And to some extent, of course, we can do that. But when it comes to volatiles like water and carbon dioxide, it's still very difficult for two main reasons. The first difficulty is that compared to gas giants like Jupiter, the formation of rocky planets can take much longer, well after the dissipation of a planetary disk. So if we want to understand how Earth-like planets acquire their volatiles, we need to understand not only how much of volatiles are contained in the building blocks, but also how those volatiles survive through many stages of planetary formation, especially high-energy collisions like giant impacts and late accretion. Also, late-stage accretion can bring icy materials from the outer solar system, so things can easily get complicated. The second difficulty is that the volatile budget of Earth is quite trivial. This slide summarizes the present-day water budget of Earth, and we of course have an ocean, which is which contains 1.4 times 10 to the 21 kilogram of water. The continental crust contains about 0.2 ocean worth water, and the mantle probably has about 1 ocean worth water. And the core is a big unknown. And according to some geochemical estimates, it could contain up to 7 oceans. But this is really uncertain. Now, 1 ocean is just 0.02% of Earth's mass. So Earth is actually quite dry. And for comparison, carbonaceous chondrites contain about 10% water, and ordinary chondrites, which are usually considered to be very dry, contains about 0.05% water. The carbon budget of Earth is similar in a sense that you don't need much, but its spatial distribution is very different. As you can see, as you move from the atmosphere, ocean, continental crust, and mantle, the amount of carbon contained in each of those reservoirs increases by a couple of orders of magnitude. So present-day mantle is responsible for most of the carbon budget, although the core can contain an even greater amount of carbon. But again, this is highly uncertain. Now, the core being a wild card, both for water and carbon, is a big problem if we want to model the volatile budget of Earth-like planets from scratch, that is, from the beginning of planetary accretion. The core could suck up potentially a huge amount of volatiles. So unless we have a really good understanding of how volatiles should be partitioned into the core, predicting the volatile budget of shallower reservoirs suffers from considerable uncertainty. Now, we can bypass this core-related uncertainty if we limit ourselves to volatile evolution after core formation, because we can then focus on volatiles contained in the surface reservoirs and the bulk silicate Earth. The mantle and the core can still interact chemically, but it's diffusion limited, so it's very slow. And so to first order, we don't have to worry about the core anymore. In the case of Earth, we have 2 to 3 oceans total and 100 to 200 birds worth of carbon dioxide. So the question is how they have been distributed from the magma ocean stage to the Hadean and Archean Earth to the present day. The primary accretion phase of Earth is believed to be ended by the moon-forming giant impact, which must have melted a large fraction of the mantle, creating the so-called magma ocean. And the right panel here schematically shows how a magma ocean solidifies. This solid line is a mantle solidus. This is depth versus temperature, and this solid line is a mantle solidus, and this dotted line is a liquidus, and this thick line is a mantle adiabat. Because adiabat is steeper than the liquidus, magma ocean generally starts to solidify from the bottom up. And this magma ocean dictates the spatial distribution of carbon and water, because carbon dioxide and water have very different magma solubilities as shown in this figure. Here, solubility is shown as a function of partial pressure. And as you can see, water is much more soluble to magma than carbon dioxide. And as a result, when you have a magma ocean, most of carbon dioxide is in the atmosphere, and most of water is in the magma ocean. So if we start with the initial budget of 100 barrels of carbon dioxide, for example, most of it should be in the atmosphere after the magma ocean solidifies. So the very early Earth must have had the Venus-like dense carbon dioxide-rich atmosphere. But in the case of Earth, we know from the geological record that by the end of Hadean, that is 4 billion years ago or so, the atmospheric carbon dioxide was probably already below 1 bar. So something must have happened to remove the massive amount of atmospheric carbon during the Hadean. And people working on the early Earth are well aware of this issue for many years. And for example, this is a figure by Kevin Zanley for the evolution of various components of surface environments during the early Earth. And note that x-axis here is time in the log scale. And it's kind of busy figure, but I'd like you to look at this, this green dash line, which is evolution of carbon dioxide. And initially, atmospheric carbon is about 100 births. That is, we have Venus-like situation. And again, this is because of degassing from magma motion. But here it drops down to almost nothing within 100 million years in this figure. But this rapid drop of atmospheric carbon is just an assumption here. Kevin Zanley and also Noam Streep have long been arguing that the massive amount of carbon dioxide must have been sequestered by rapid plate tectonics in the early Earth, which may sound possible because the early Earth was hotter than the present day, so it could have been convecting more vigorously than today. But plate tectonics wouldn't necessarily be faster when the mantle was hotter. And this is actually what I worked on some time ago. And if you think about how mantle melting associated with mantle convection affects the tempo of plate tectonics, we have to arrive at somewhat counterintuitive conclusion that the hotter mantle has to convect more slowly, not more quickly, as indicated by this thick line. This left figure shows the how surface heat flux should vary with the mantle temperature. And this star, this guy, represents the present day situation. And for hotter than present day mantle, the heat flow is lower, meaning that meaning more sluggish plate tectonics. And this heat flow scaling, however counterintuitive it may be, is supported by the geological observation of how the mantle has cooled down, as shown to the right. These dots here represent, this is actually this vertical axis, the mantle potential and temperature shown as a function of age. This is 0 and this is 4 billion years ago. And these dots represent petrological estimates on the potential temperature of the upper mantle. And to explain this concave downtrend of thermal history, you need to have a heat flow scaling like what is shown to the left. But as you can also see here, this geological constraint goes back only to the mid-Archean. So we could still have rapid plate tectonics in the Hadean, but why we should have it has long been unresolved. Now, we have virtually no geological data about Hadean mantle dynamics, but we can still make use of temporal continuity. That is, the Hadean started with the solidification of a magma motion. So if we better understand some details of how a magma motion solidifies, it may give us some clues on Hadean mantle dynamics. And this is how my former student, Yoshi Miyazaki, and I started to work on magma motion solidification a few years ago. And this is obviously very difficult problem with lots of uncertainties. And even though we think we did a fairly good job of modeling things with entirely consistent thermodynamic calculations, how a magma motion solidifies depends critically on grain growth kinetics, which is still very constrained. What is shown here schematically is 4 end member cases we considered in this paper, depending on the grain size in convecting region and the grain size in solid matrix. And what is most striking is that creating a chemically heterogeneous mantle at the end of magma motion solidification is quite likely, like 3 out of 4 cases, and because of Rayleigh-Taylor instability associated with the solidified magma motion. Now, this chemically heterogeneous mantle could give rise to a very different kind of mantle dynamics. If the mantle is chemically more or less homogeneous, as we usually assume, the upwelling of a hot pyritic mantle in the past should have produced a thick basaltic crust as well as thick depleted lithospheric mantle, as shown to the left. And this thick depleted mantle is also very viscous because it's devoid of water, and this is what slows down plate tectonics. Okay, but if the mantle is chemically heterogeneous, or more specifically, as shown to the right, our thermodynamic calculations suggest that small-scale iron-rich blobs are embedded in a high mg number matrix. Then the melting of such a mantle is actually more limited than this pyrolytic case, resulting in a much thinner depleted lithosphere, and plate tectonics can be quite rapid. And we quantified this new kind of Hadean geodynamics in a recent paper published last year. And for example, this figure shows how plate velocity changes with mantle potential temperature. And this black curve is for the conventional homogeneous pyrolytic mantle. It's kind of similar to the heat flow scaling I showed earlier. And this red curve is for the chemically heterogeneous mantle. And if you compare these two cases at Hadean-like situations, like 1600 degrees Celsius, you can see plate tectonics with the heterogeneous mantle is about 10 times faster than plate tectonics with a homogeneous mantle. And this rapid plate tectonics can sequester a large amount of carbon dioxide in the early atmosphere and make a habitable environment in the Hadean. Note that the time axis is again the log scale, and left panel shows the carbon dioxide concentration in the atmosphere, and in red, those red curves is about the carbon dioxide concentration, and the right panel is a corresponding surface temperature. This red dashed line is a case with the kind of mantle we have today, the homogeneous mantle. And in this case, carbon sequestration takes place more than 1 billion years. So surface temperature remains above 200 degrees Celsius for the first 1 billion years of Earth's history because of the greenhouse effect. But this is obviously inconsistent with the geological record on the Archean PCO2. But if you had a chemically heterogeneous mantle, you can have rapid plate tectonics, which can sequester carbon dioxide 10 times faster, so within about 200 million years in this case, in this particular example. And that's for the fate of carbon in the early Earth. And now I'd like to turn to water. As I mentioned earlier, most of water is in the magma ocean. And when the magma ocean solidifies, water in the magma ocean is actually frozen in. And this is a very important point because many previous studies of magma ocean solidification assumed that water in the magma ocean will be eventually all degassed upon solidification. But that requires purely fractional crystallization, which is very unlikely to take place because of the so-called rheological transition. The rheological transition, which is indicated by this dashed line here between the solidus and liquidus, refers to the fact that the viscosity of a solidifying magma jumps from liquid-like values, very low values, to solid-like very high values. So when magma is cooled below this transition, variecal mixing, so vigorous magma convection stops, but still variecal mixing takes place due to the Rayleigh-Taylor instability. And this Rayleigh-Taylor instability effectively traps water in a solidifying magma ocean. Now, if you think about how a magma ocean ends and what's going to happen afterwards, it probably goes like this. This cartoon shows the very final phase of magma ocean solidification, in which you still have a little bit of a melt layer left, which hasn't experienced the rheological transition yet, just above the rheological transition. And when the surface reaches the rheological transition, this is the end of vigorous magma convection, and the whole thing just stops. But we still have a leftover melt phase in the top 200 kilometers or so, which contains lots of water in it. And because of its buoyancy, this melt phase percolates upward. And degassing associated with this melt percolation creates the early ocean, which is not so deep, probably much less than 1 kilometer deep, because this represents just the amount of water contained in the top 200 kilometers of the mantle. And if you wait even further, we eventually transition to subsurface mantle convection, which can degas water in the mantle to the surface, gradually deepening the ocean. And just to summarize what I talked about so far, magma ocean solidification results in a massive carbon dioxide-rich atmosphere and a very shallow ocean. And the initially wet and chemically heterogeneous mantle allows rapid plate tectonics in the early Hadean, which can sequester atmospheric carbon quite efficiently. And this is at least a dynamically plausible and also self-consistent scenario, because the formation of early ocean, even though it's probably very shallow, still makes it possible to have plate tectonics. And something like this has to have happened to be consistent with the geological constraint on the Archaea and PCO2. But it doesn't mean it will always happen for other, rocky planets other than Earth. So if, for example, if we have more carbon and less water degassing associated with melt percolation at the end of magma ocean may not saturate the atmosphere with water vapor. So a water ocean wouldn't form and plate tectonics may not start. So depending on the initial budget of carbon and water, rocky planets can take very different evolutionary paths. And we explored this idea in another paper published last year, and this is a summary figure from the paper. What we are showing here is whether a rocky planet can have a surface, a water ocean or not, as a function of initial carbon dioxide concentration in the mantle, which is on the x-axis, and the initial water concentration in the mantle, which is on the y-axis. And this top row is for the 1 Earth mass, and the bottom row for 5 Earth mass. And the left column is for the stellar radiation of 330 watt per square meter, corresponding to the early Venus situation. And the right column is for the early Earth situation. And this region, this white region marked by oceans form t equals 0 means that the ocean form right after magma ocean solidification due to melt percolation. And even if a planet starts with stagnant lead convection with no surface ocean, it can continue to degas water by hotspot magmatism. So if that type of degassing is more efficient than hydrogen escape to space, then if we wait long enough, an ocean can eventually form. And this possibility is indicated by these contours. This contour, 0.5 G a billion years means that ocean form eventually after 0.5 billion years of planet formation and so on. And this gray region denotes the ocean doesn't form even by waiting for more than 5 billion years. And this gray rectangle shows the likely range of carbon and water budget for Earth. And interestingly, ocean formation seems to be guaranteed, and with this budget, by the way, with this budget, ocean formation seems to be guaranteed for the early Earth, but not quite so for Venus. And this trend is enhanced with greater planetary mass. And we speculated that this might be able to explain why Venus and Earth evolve in very different ways. So if we summarize, we could say the approach based on mantle evolution can bypass core-related uncertainties, but this approach depends critically on initial volatile budget. So the real question is how to get this initial volatile budget, which brings us back to square one. And we really need to face the complexity of volatile evolution during planetary formation. And as I mentioned earlier, one of the main difficulties of modeling volatile evolution from scratch is volatile partitioning into the core during planetary formation. At first sight, this may be daunting, but it may not be so bad because metal silicate equilibrium during core formation also affects other chemical systems such as the hafnium tungsten and uranium lead isotope systems. So it may be constrained in some way. The other major problem is how much volatiles would escape, be lost to space during planetary formation. And this is a problem of atmospheric evaporation. And for the rest of my time, I like to talk about this briefly. So giant impacts create magma ocean. So the surface is, of course, hot enough to completely melt rocks, like few thousand kelvins. And now if you look at the impact simulation, the surface temperature is not just a few thousand kelvins, but it can be as high as 10,000 kelvins. And this is really hot. And this fundamentally modifies the thermal structure of the atmosphere, which can lead to the substantial loss of volatiles. This atmospheric mass loss due to high internal temperature is a very popular concept in exoplanetary science, known as core-powered mass loss. I'd like to note that the core here refers to the condensed part of planet, including crust, mantle, and metallic core, not just the metallic core. Anyway, so core-powered mass loss is a popular idea because it's one of the mechanisms proposed to explain difference between super Earths and sub-Neptunes. That is the famous bimodality of radii of small exoplanets. So there are many papers about this, but it turns out it's difficult to find a paper that describe all possibilities with this core-powered mass loss. For example, this cartoon is taken from the work of Gupta and Strickling, and their model atmosphere shown here always assume that always have a convecting region, this light gray, and the radiative region even further light gray. But this type of atmosphere is not always guaranteed. So my postdoc, Darius Modiros-Dagarian, and I recently wrote a paper about this. And in this paper, we suggested that there are at least 3 regimes of atmospheric evaporation for rocky planets, depending on internal temperature. Regime 1, shown to the left, has the highest temperatures. And because of that, the Bondi radius, which marks the edges of the atmosphere, is very small. So we have only a convecting region. And regime 2, shown in the middle, has lower temperatures. So Bondi radius is greater. And in this regime, we have both convective and radiative regions. And at even lower temperatures, at regime 3, we also have a conducting region on top of the radiative region. So the thermal structure of a planetary atmosphere varies considerably with changing internal temperature, and this affects the efficiency of atmospheric mass loss. And this is a sample calculations for a hypothetical exoplanet with 3 Earth mass, hydrogen-rich primordial atmosphere with a 1% planetary mass. So this is a very massive primordial atmosphere, and the equilibrium temperature of 500 K and XUV flux of 0.1 watt per square meter, a typical early solar system value. And the horizontal axis here is a surface temperature, and this is 1,000 K and goes up to 10,000 K, and here is a 2,000 K. And the vertical axis is a mass loss in kilogram per second. This thick line is a prediction, and we are also showing other traditional estimates like energy limited, core-powered, and hydro-based. And this hydro-based approach is valid only for regime 3, where you have a thermosphere. And in this regime, our prediction is similar to hydro-based estimates. In regimes 1 and 2, on the other hand, the prediction is much higher than the energy limited estimate by a few orders of magnitude. And some of you may get the impression that we may be violating some kind of physical bound, but we're not violating anything. This energy limit estimate is about mass loss due to XUV heating. So it doesn't take into account mass loss due to internal energy. Energy limit estimate shown here still depends on surface temperature because this estimate depends on still depends on boundary radius, which in turn depends on surface temperature. Anyway, the details aside, what is interesting about this is that this business of atmospheric evaporation with high surface temperatures is still in a state of flux, and we are planning to apply this new theory to the early Earth and the early Venus to see what comes out. Maybe we see something quite dramatic, so please stay tuned. Okay, so to wrap up, the evolution of terrestrial planets depends on the initial volatile budget, the spatial distribution of which varies by magma ocean formation and desalination, and then by subsurface mantle convection, either stagnant lead or plate tectonics. And modeling the initial volatile budget from scratch requires a better understanding of at least the two things: the volatile partitioning into the core, as well as volatile escape to space during stochastic high energy planetary accretion. So there are lots of interesting things to do in this regard, I think. And that's it. Thank you.
Thank you so much, Korenaga-san. Very, very fantastic talk and very interesting result. So now we move on to the Q&A and the discussion part. So participants, if you have any questions, comments, discussions, please raise your hand on the Zoom button or type your question into the chat box. Either way is fine. So while people are thinking about their question, I would like to ask one question. So you introduced considering the realistic physics, the solidified mantle may be the heterogeneous. And my question is, can we test such scenario with the existing data for the early Earth, or do you expect to testify the scenario with the future geological, geochemical studies?
Yeah, that's a good question. So it's more, right now, it's more like proof by contradiction. So if you don't have it, then it's really difficult to have. Oh, by the way, so it's kind of interesting because if you are familiar with geology literature, people are not, still debating when plate tectonics started or not. And so, the popular idea is sometime in the Archean and Hadean would be stagnantly. So the notion of plate tectonics is, people are happy with plate tectonics from mid-Archean, but not so much for the, for the Hadean or early Archean. But the problem is, even if you have regular plate tectonics, like with homogeneous mantle, you cannot sequester atmospheric carbon quickly enough to draw down the PCO2 below 1 bar. So that's we are two different kind of issues. But even if you have plate tectonics in the Hadean, if you have homogeneous mantle, then it has to be slow because we think we have a reasonably good understanding of how plate tectonics with homogeneous mantle should work from the past 3.5 billion years of geological record. So then, but if you cannot have it, then you need to have something else. And then if you think about magma ocean, so from a theoretical point of view, it's quite straightforward. But how to test it is, I think the problem is we really need to have a good understanding of what could happen with this mantle convection with chemical heterogeneous like lithology, because it's because the thing is, if you start with chemical heterogeneous mantle, this should eventually transition to chemical homogeneous mantle by mantle mixing. But during this transition, what kind of igneous product we have keep changing because at the very beginning, we have those two lithologies, a high imaging number matrix with a small ion-rich broth, and we can calculate that. But once you melt them, once you make those different kind of Hadean oceanic crust, and then you subduct it, and then you need to think about the melting of different kind of rocks, and this keep ongoing for probably a few 100 million years. And I think, but still, we need to model, and we need to have a reasonably detailed theoretical understanding of what could happen with this kind of mantle, so that we can compare with, for example, geochemistry. Because if you know how, I don't know, we have an expert on this issue in the audience, but that if you're familiar with how people do it, geochemistry is that, because geochem can contain certain amount of trace element, and by looking at trace element systematics and then compare with that, if you look at mid-ocean ridge and the arc and different kind of arc systems, and you can classify geochemistry into different tectonic regimes, right? But this interpretation assumes that we have a kind of modern style plate tectonics. But if we have defined plate tectonics with different kind of chemical heterogeneities in the mantle, even if we have subduction, maybe subduction zone signature could appear in a different way. So, but unless we model what kind of igneous product and what kind of geochemical signature should be associated with it, it's hard to make that kind of comparison. So for Hadean time, for foreseeable future, we only have geocon, so we need to rely on some geochemical interpretation of geocon data, but to do so, okay, we need to bring up our level of theoretical understanding of this new type of Hadean geodynamics. So at the moment, I'm not sure, but that I remain hopeful. Yeah.
Okay, thank you very much. So we need more the theoretical prediction for what could happen on such kind of heterogeneous matter to better interpret the geochemical. Thank you very much. All right. So audience, do you have any questions, comments? Please raise your hand and what type of. Okay, Tim, go ahead.
Yeah, I was waiting if maybe someone else wants to ask first. So yeah, thank you so much for this very interesting talk. Really enjoyed it. My question, I have many questions actually, of course, but my most important question, I think, is, so you said specifically with regards to the crystallization of the Earth magma ocean that the nucleation of the crystals is and you singled it out specifically, nucleation of the crystals is the most important aspect that sets the crystallization timescale. And I was wondering really if you can confidently say that, given that so many different things interact at the same time in such short on such short timescales with each other. For instance, that the atmospheric thickness really sets the heat flux. And that all happens while, like at the base of the magma ocean, different things happen. The chemical evolution is so poorly understood. So I was interested in your opinion on if we are really already at the stage where we can say what is the most important parameter, or if we cannot. Yeah.
So I think in terms of time scale, whether or not you have a batch crystallization or fractional crystallization doesn't really matter much. So because magma ocean, the upper part of magma ocean at least has to be, should be convecting very, very vigorously. So vigorous convection means very rapid cooling. So it kind of cools down quite rapidly. but what kind of chemical differentiation should take place within solidifying magma motion depends a lot on grain size. And so how, because Soronov worked on this a while ago, and there's like really no progress about this. I mean, just zero progress. And so because because it's about the lower mantle, lower mantle issues and things just depends on really subtle details. And that, I think you are familiar with the scaling analysis, and it's just like that, at the borderline, both equilibrium and fraction crystallization are possible. So it's quite tricky. So that's why we tried all possibilities in our paper, 4 end member cases, and we tried all of them. And what the most robust conclusion from it is that the chemical heterogeneous mantle is highly likely. Okay, because if you have a batch crystallization, you have to be in a quite tight, tightly constrained parameter space. So yes, and right. So and then actually the other student of mine worked on the possibility if we can constrain on this grain size issue by looking at the possibility of basal magma motion. So basal magma motion forms. Oh, by the way, so I'm not sure the audience noticed that this basal magma motion stuff is, if you look at the mantle liquidus and the cooling mantle adiabat, the original basal magma motion idea is that this adiabat gonna touch the liquidus at the mid mantle level. So magma motion solidify from mid mantle, from both upward and downward. So this gonna leave the basal magma motion not just top but also at the bottom. But this idea is a little with a problem, because if you calculate mantle adiabat, it also curved as a liquidus, so it wouldn't touch the liquidus at mid mantle level. So mantle should start, as far as our understanding of thermodynamics of mantle melting is concerned, magma motion should still crystallize from the bottom up. Okay, but if you have a large grain size in the solidifying magma, then you have an efficient melt percolation. And because at the lower mantle, lowermost mantle conditions, melt is denser than the solid. So melt percolates downward, and this creates basal magma motion. So then we try to constrain the thickness of initial basal magma motion reflects the grain size. So if you have a better understanding of this hypothetical basal magma motion evolution, we may be able to constrain grain size, and we did that. And I think we didn't get a good constraint. So that's a tough problem. So if anyone has a better idea to constrain this grain size problem, that would be very important, I think. Yeah.
All right, thank you. Any other questions, comments, discussions? Another question I would like to ask is that if I remember correctly, in your another work, I think you have proposed much, how to say, larger amount of the oceanic water during the Archean based on the discussion, the continental freeboard.
Freeboard, yes.
Consideration. And but today's talk, you said that Earth may have started from the shallower the ocean, so it means that the mantle needed to first degress large amount of water to match the sea level at the Archean. Then the oceanic water needed to be transported back again to the mantle. My question is, my understanding is correct, and if that is correct, do you think that it is plausible in terms of the mantle dynamics?
Oh yes, yeah. So that's so in 2017 paper, that freeboard work, we're kind of just going backward from present day, and so in that paper I speculated, if this trend continued, we have a deeper and deeper oceans, and so that was my thinking at that time. I tried to find better, just a moment. So try to find appropriate figure. Yeah, so that's my, okay, so this let me play, oops, just let me play this. So my current thinking summarized by this one. So we have a reasonably good constraint on from geological record on content of freeboard back to about 2 to 2.5 GA. Ocean volume has to be increasing like this, and then beyond that is just a sheer speculation. So I kind of because there is no other reason to reject the possibility. So I'm gonna keep going like this. But because of our recent magma ocean work, it wouldn't keep going like that. So it has to start from shallow. So now for this first few hundred million years or so, we have a different kind of mantle. So we can have a very rapid plate tectonics. So the residence time of oceanic plate on the surface would be short, like 10 million years or something like this. So it doesn't have much time to absorb water. So it's more like degassing dominated. So things keep pumping out of the mantle. But then when things are well mixed up, and then if you recover pyrolytic, like modern type mantle, then we need to transition to more sluggish plate tectonics. So then we have more time to hydrate oceanic crust and the oceanic mantle. So things can switch to the regassing dominated regime. So that's that's my current thinking. So yeah, so that's kind of I had to change my idea because of this magma ocean work.
Okay, thank you very much. There is the one question in the chat box. Chanda, do you want to read by yourself?
Sustaining a thin layer of magma ocean below surface near the compression magma ocean in bottom acidification with the presence of tectonics. Interesting. So sustaining a thin layer of magma ocean below surface near the compression. So what? I'm not sure what kind of why. Yeah, I like to understand the motivation behind this question. So why we have volcanic eruption on Earth, maybe like a partial melting, partially molten zone beneath the surface, I guess. partially molten subsurface, I guess. So let's see. So so what should I say? So I would say, if I go to the, where did I? So if I go back to this slide, I'm gonna share this slide once again. No, just a moment. So if we share this way, yes. So okay, so that's the end of surface magma motion, and then so you know, those melt, gonna go up and erupt, and then you have a, this is a kind of like a crustal thing, like erupted melt, and then this is depleted stuff. And so at this point, okay, so because this is depleted, okay, so this solidus is for the undepleted, unmolten mantle. So even though this adiabat is above solidus, it doesn't mean it should be molten, because all those melter, you know, escape. So this this line, this adiabat is on the new solidus of this depleted mantle. Okay, so I'm not sure you get it, but anyway, so there's no melt here, and then all melt is, you know, erupted like that. Now, of course, you know, if you wait, okay, so that's the right after the magma motion solidification. But if you wait like 10 million years or so, the thermal boundary layer, of course, and because and after that, surface temperature goes from like 1600 K to 500 K because of the collapse of magma motion atmosphere. So surface boundary layer grows, and if you wait probably 10 million years or so, you can initiate the sublisospheric convection, and then you can have like a regular, like, you know, of course, mantle goes up and then melts. This, you have a partially molten zone beneath upwelling region. So, but if you don't have any, you know, if you have a, you know, let's say if you have stagnant leads, then you also need to have mantle upwelling to have a partially molten zone. So without, you know, you wouldn't, I think it's kind of hard to imagine kind of a near permanent presence of partially molten zone with no reason, because of melt buoyancy, because things just gonna go up and erupt. I have another hand question.
Yeah, you can go ahead.
Thank you very much for a very interesting talk. If the time permits, I'd like to hear more about the atmospheric loss, the new result of 3 regimes of atmospheric loss. Yeah, I think I have many questions to understand better, but will you explain again why in all 3 regimes the rate, atmospheric loss rate, is a few orders of magnitude larger?
Oh yeah, not all. Okay, not all. Hydro-based regime 3 is a, you know, is quite comparable, but this, because okay, so hydro-based model is only applicable for regime 3, so you cannot use this for 2 and 1. For 2 and 1,
is this hydro-based? Does the hydro-based? What does the hydro-based mean?
It's more like solving the fluid mechanical equation for it, like hydrodynamics based calculation.
Okay, so is it hydrodynamic escape?
Yeah, right,
okay.
Yes. But this energy limited and core powered is more like kind of formula, kind of like energy, like how much of energy you have, it's kind of bounding approach. So energy limited approach. So even though we are showing as a function of temperature, but energy limited approach doesn't really care how hot the planet is. So energy limited approach is just about is a mostly a function of XUV flux, and if you have a higher XUV flux, you have a you take that, of course, you multiply some efficiency, like energy conversion efficiency factor. So you take some amount of incoming XUV flux and use that to make atmospheric loss. Okay, so and this depends on the two factors. So one is this XUV flux, and the other is at what altitude this mass loss takes place. So this is called bonded radius. So bonded radius also. So we kind of try to do our best to make use of existing approach. So energy limited, it depends on XUV flux, which we have a constant value, but also depends on bonded radius. But bonded radius, as you can see, that this dashed line is the bonded radius. The bonded radius changes with internal temperature. So by changing surface temperature, you have changing bonded radius. So you can still apply the formula derived for energy limited escape, but because energy limited escape is just due to the XUV flux, so that's a kind of a main reason for this large difference in this prediction. And the core part mass loss is much, of course, these two things actually, core part mass loss is applicable, I think basically for regime 2, but you can kind of tweak things to apply for regime 3, but most for regime 2, where you have a radiative and convective regions. So, but the traditional core part mass loss applied another energy limited bound on the how much of mass loss can take place, and this is but this bound is really difficult to justify. So that's the main reason for this huge discrepancy between those two estimates.
I see. And yeah, so recently, I mean, these energy limited, so the Fulton gap has been observed for exoplanets, but is it insensitive to, I think the detailed population would be sensitive to some atmospheric loss rate, maybe, but the approximate feature of Fulton gap would not be sensitive to this mass loss rate.
Oh, it's actually sensitive to. Okay, so this is
yes.
So this actually, example shown here is for the 3 Earth mass, and this is, of course, if you change this core mass, where you have regime 1, 2, 3 also changes. So there's a critical. So we actually applied to this bimodality problem, and actually, I saw the 100. We submitted. We have paper in review. But anyway, so this we found that kind of notion of critical planetary mass, and if planetary is above certain mass, then I think it's hard to get into regime 1 or 2. So you end up with you end up with it, keeping the most primordial atmosphere. But if planetary mass is smaller than the critical mass, then it's easy to get into 1 and 2. So you lose almost all mass because of this high atmospheric mass loss. So it's, I think it's this, we applied it to this bimodality problem, and it seems to work, at least.
Thank you very much.
Okay, thanks for the discussion. Because we are running out of time, I'd like to close the discussion at this point. So thanks again for the fantastic talk, the June. Thank you very much.
Thank you very much. Thank you very much. Okay.
And there is a very short announcement for the attendees. So the next Rocky World discussion will be held on the June 1st, again on Thursday from 1 p.m. UTC. And the speaker is Megan Newcomb from the University of Maryland. And topic is about the planetary and volatile delivery. I think this is also related to today's topic. So looking forward to see all of you there in a month. So thank you for all attendees for today and see you. Bye.